Hey, welcome back. So for the last few months, I've been using Apple MLX quite heavily. Now, if you've never heard of Apple MLX before, it's Apple's machine learning framework. Think of it as an equivalent to numpy and pytorch all in one. Now, it's specifically designed for Apple Silicon and getting the best out of the GPUs on your machine. So if you're doing anything like fine-tuning a large language model, or if you're doing inference on an LLM on your machine, chances are it's probably using Apple MLX underneath the hood. So today I'm going to give you a bit of a tutorial on how to use that. Now don't worry if you don't have an Apple device, because everything that I show you today you can equivalently do in both numpy and pytorch, and I'll show you that as we go along in this video. But don't worry, I'm going to keep it super simple. We're not going to go into the training of large language models, but I'm going to show you all of the functions that you will probably need to get that deeper understanding of LLMs. Everything from handling vectors, handling matrices, being able to shape things. Now don't worry, I'm going to keep this super simple, but hopefully it'll give you a better understanding as we go deeper later on in other videos. So the first thing I want us to get familiar with is probably vectors. So on the screen here, I've got a super simple vector. It's got essentially 5 numbers. It's a one-dimensional row vector. Think of it as the equivalent of an array. It's just got the numbers 10, 20, 30, 40, 50. And actually, if I was to do this within Python today, I could do this with a simple list. So I can just do something like touch scratch.py, and that will create our code file. And now if I was to type in something like a equals 10, 20, 30, 40, 50, which is the exact same array that we saw 2 seconds ago, and then just did print a, and then we come back to our terminal and we run python scratch.py, you can see I'm just listing out the elements of that array. Of course, I'm not really using any GPU at this point. That's just a CPU based operation. But if I wanted to work with that in the GPU, then I can actually just install Apple's MLX framework. So to do that, I will just type in pip install MLX. And as you can see, it's already installed in my machine. So it makes it nice and easy now for me to use this. So actually, if I come back into this and then I just say import MLX .core, and we'll do it as mx. That is all I need to do to import MLX into my Python file. And then I can just change this. So rather than doing a equals a list here, all I need to do is type in mx.array, and then we can just close some brackets around here, save that. And then if we run this one more time, you can see now I've got the equivalent in Apple MLX. The major difference here is this is now working with the GPU. And as you can see, it's returned back that array, plus it's also came back with the underlying data type here, which is an int32. It is really that simple to get working with Apple MLX. Now, of course, if I wanted to, I could print the shape of the array. So I could just do something like print a.shape. And then if I run that one more time, so you can see 1, 2, 3, 4, 5 elements within that list. And again, if I wanted to print the type, I can do the exact same thing. I can do a.dtype, and then that is going to come back with the type of the array. And you see it's came back with MLX core.int32. Let's just put that back to A. And then if we run that one more time, I can see the vector here, 10, 20, 30, 40, 50, plus the type in1. Now, if I wanted to change the type, it's really simple. Rather than returning an int32, I could obviously just make this to something like mx.int16. And now when I run this, you're going to see it's going to come back with an int16 in that sense. I could select something else. I could select float32, for example, and then if I run that here, you can see the type is 32. You still see I'm getting 10, 20, 30, 40, 50. But of course, if I put something like 10.2 in there, run that one more time, you see there's 10.2 there, blah, 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 blah. Of course, if I don't specify a type and then I leave 10.2 within here, you see it's going to automatically infer that it is a float 32 in this case. If I move this back to 10 there, run it one more time, you see it's back to being an int32. So it will automatically default to int32, but I can control that with the types. And I'll come back into that a little bit more later. So far we've seen a one-dimensional row vector, but actually I can do a column vector as well. So rather than it essentially being an array of 10, 20, 30, 40, 50, across as a row. I'm going to do this as a column here. So 10, 20, 30, 40, 50 is now the columns. Okay, so let's come back to our Python file for a second, and then let's look at how we can represent that. Currently, we've got this as a row vector, 10, 20, 30, 40, 50. So to change this into a column vector is pretty simple. I just then need to go 10, 20, 30, 40, 50, and put square brackets around each one of these. And then, of course, I'm going to have to surround the entire list with a set of square brackets here. And now if I wanted to, I'll not just print the array, but I will print the shape, and I will print the type as well. So we'll just put dtype in here. And now if I come back into my terminal, run this one more time, you can see it's now as a column vector, 10, 20, 30, 40, 50 there, it's separated. And you see the shape has changed here. So as you can see from the shape there, it has changed. Previously, it was essentially a row vector. It was horizontal. There was just 5 elements. There was a single row, and you can now see that there is 5 columns, and then within that there is a single dimension per row there as well. Now, as I said before, I could do the exact same thing in numpy. So if I just comment out this for a second and I do import numpy as np, you're obviously going to have numpy installed. You can do that by doing pip install numpy. I've already got that installed, so I'm not going to bother. But all I would need to do is change the mx here to np, and then I can run that one more time, and you see it comes back with the same answer. In this case, it's obviously using a different type here. You see it's defaulted to int64. Also, numpy is using CPU rather than GPU, but all of that is equally fine. So I have equivalence with numpy. There are some differences in the framework, but probably not enough for you to care about too much. So pretty much think of Apple MLX is a bit of an equivalent to numpy, except you're using your Apple Silicon and GPUs as opposed to CPU. Again, if I wanted to prove this, there's actually a really sort of very cool tool. It's called Acetop, which allows you to monitor your GPU and CPU usage on your Apple device. So if I do a pip install Acetop for a second here, you'll see that's already installed on my machine, as you would imagine. But then if I do sudo Acetop there for a second, and you see I've got this very cool display here, and it shows me roughly what my GPU usage. If I just kind of run this one more time, Python scratch, you see it's nothing is happening with the GPU because it's all happening on the CPU. If I bring this back here to using Apple MLX for a second, now these are so quick that you're probably not going to see much of this, but if we just run this for a second, you can see a little bit of a kind of push there. It went from 5% to 6% to 7%. You know, so you see a bit of push. You can see I'm sort of hitting the GPU there. Again, it's not much to make a kind of difference, but you get the idea that I can see that I'm using my GPU usage. Now, this is a very cool tool. So later on, when you start to get into things like fine-tune or look at inference, actually using this tool is really cool to just be able to understand how your GPU is being used. But I'm going to get rid of that because we don't need that anymore. Now, if I want to, I can, of course, just access the array like I would normally. So rather than maybe printing everything out, maybe one of the things that I would want to do is just loop through this. So I can just do a for x in range, and we'll just access a.size, which is a is obviously representing our mx array here. By the way, that's sort of the equivalent, that load here. So mx array in this sense is the equivalent of a pytorch tensor. So I've loaded this into effectively a tensor at that point. And then if I want to just loop through this, I'll just do a normal for loop. And if I want to print it, I would just print it out like any other array. So I would just do a print, and we'll say a, and then I'll put x within my square brackets here so I can access the index item. And now if I were to run this one more time, you can see 10, 20, 30, 40, 50. Now what is super cool about this is it supports in-place updates. So I could just do ax is equal to ax plus 5. And now as I'm looping through this, I can just update the value. We run this one more time. You see it's now 15, 25, 35, 40, 55. And then the important thing here is you see at the bottom, I've just printed out the array. You see the +5 has happened. So it's done an in-place update. I've not created a copy of the array. I'm able to just do in-place updates if I want to. Now this is obviously not best practice. So if I am wanting to do an update in this array, then actually it's a waste of the framework, me looping around like this. I'm not making best use of my GPUs. So I'm going to show you how to do some quick calculations, some vector calculations, etc. on using MLX. So in this case, I've loaded my array as I did before, but if I want to add a number, then the simplest way for me to do this is to do mx.add and then just pass in the array that I want to modify. So in this case, it's A. And then I just need to put in the value that I want to do the addition of. So in this case, I can put in an input array. I'll show you that in a second. But if I want to, I can just put a scalar value. So if I want to add, let's say, 5 to everything, and then obviously I just, rather than printing out A, I'm going to print out my new array, which is C. And then if I just run this one more time, you can see it's now 15, 25, 35, 45, 50. Of course, in this case, because I've done an add and I've returned an array, if I do a print A in that sense and then run this over here, you see 10, 20, 30, 40, 50. That's not been updated, so A is still as it was, but it's only the C array that has got the added version. Now, of course, it's not just addition. I can do the same for things like subtraction. So if we run this, same sort of thing. We run this one more time. So you can see here, the original array is 10, 20, 40, 50. If I minus 5, it's 5, 15, 25, 35, 45. Again, very, very powerful stuff. You can imagine that when you have to do this against very, very large batches of numbers, it's going to be way more efficient than trying to do this with CPU. Just being able to do a batch update across the array is really where this is going to excel. Again, I'm working with integers at the moment, but this equally works for floats as well. So if I was to, let's just put some numbers in here. So if I do 20.3, 30.4, 40. And we can put some different numbers in here as well, because this is really where GPUs get into their own. And then you can see it works, and we're using it against float 32 in this case, and it's done the magic. Now, this is one of the key things that you are going to be doing pretty much all of the time. So additions, subtractions, multiplications, when you do working with machine learning models and MLX frameworks, when you sort of tune your own models, that's kind of one of the key things that's really happened. Now, I'm just going to switch this back to being integers for a second to keep it simple. So we've done additions, we've done subtractions. You can imagine that multiply is going to be supported. So if I clear this and then do the same one more time, you can see it's now multiplied everything by 10. And of course, we wouldn't be complete without divide. So we just run that one more time, and you see it's divided everything by 5. Okay, so we've now got the sort of basics of being able to do operations. So we can sort of manipulate the array. We can do calculations, add, subtract, multiply, divide. Now, the other thing that you're going to want to be able to do is do some level of reduction, i.e. you want to be able to sum all the elements in an array. You want to do a min, a max. You want to do the mean. Again, really, really simple here. So all I need to do in this case is, rather than doing a divide, I can do a sum. And again, similar, I'm just passing in my original array here. And then if we run this one more time, you can see 10, 20, 30, 40, 50. And if I add them all up, they're going to come to 150. And again, that will work for floats just as easily. If I want to get the minimum value, min should, in this case, should be 10. If I run this one more time, you're going to see it's going to come back with 10. You can imagine that if I want the max, I can do the exact same here. We'll just change this from min to max. We'll hit save, run it again. And you see it's now taken the maximum value, which is 50. And again, I can do things like mean. So if I do the mean of this, you see the mean is going to be roughly 30 in that sense. So at the moment, I'm keeping this super, super simple. I've essentially got very small single dimension vectors. But of course, if I was to multiply this up into an LLM, and I'll show you that a little bit later on, some of these vectors are going to be massive. They're going to be having a huge number of dimensions. And of course, this is going to be able to do this at speed and scale, and it's going to be able to do this across batches and really sort of push the power of the GPUs, whereas kind of CPUs is going to struggle. Now, of course, if you were not using Apple MLX, if you were on sort of an A100 or an H100 or something like that, you would be doing the equivalent things with PyTorch. That is sort of equally fine. These same concepts absolutely apply. Maybe the difference in this case with a PyTorch is you would be using a tensor as opposed to using the array, but pretty much everything remains the same. Now, of course, adding a number, etc., is probably not so exciting, or multiplying a number. One of the big things that I want to be able to do is sort of essentially add or multiply two vectors together. So if I take this example here, I would have two one-dimensional column vectors, one with 10, 20, 30, 50, which is what I had before. And then if I had 60, 70, 80, 90, 100, and then I would to add those two things together, what I would want is essentially a third array, which would have 70, 90, 110, 130, 50. And that is the 10 plus the 60, the 20 plus the 70, blah, 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 and then the result in there. I really just want to be able to pass in the two vectors together and then have it work the magic. Now, to do that, what I could do is just load an array. I'm going to make this column. We did rows earlier, so I'm just going to change this up a little bit to be columns. So I'm going to say we'll have an array. We're going to have 10, 20. So now that I've got my column vector array here, if I want to have a second array, all I need to do is just modify these numbers. So it'll be now be 60, 70, 80, 90 and 100. And of course, if I want to do an addition like before, where I passed in a and then I passed in the value that I wanted to add, which was a scalar in this case, so I added 10. Now I can just pass in the other array, so it will now automatically do 10 plus 60, 20 plus 70, etc. So now if I were to run my Python program again, you can see 10, 20, 30, 50, and now it's doing 70, 90, 110, 130, 150. So it's added the two things together. And again, point is, it doesn't care whether it's kind of a row or it cares if it's a column. It will automatically handle this underneath the box there. Similarly, if I wanted to do a subtraction, I could do the same thing. We'll just clear this. We'll run this one more time, and now it's subtracting. And it's minus 50, minus 50, minus 50. And that's because 10 minus 60 is obviously minus 50. 20 minus 70 is minus 50, kind of across the board there. Again, it equally works with row vectors. I'm going to switch it back to row vectors for a second, just because it's easier to see on the screen. And if I run it one more time, you see it came back with the exact same answers and it's shaped properly, etc. So minus 50, minus 50, minus 50. Again, if I wanted to do something like multiply, that will equally work as well. We do that, and then obviously 10 multiplied by 60 is 600, 20 multiplied by 70. Actually, let's just add, we'll print B there for a second as well so we can see the calculation a little bit easier. Run that one more time. And there you go. So 30 multiplied by 80 is 2400. 50 multiplied by 100 is 5000. So that all works well. And again, it's going to do it super fast. And again, in large language models, you're probably not going to be dealing with integers too much. It's going to be more of floats, but same thing works over and over again, right? That's what GPUs are good at. So I want to get a little bit more complex for a second. What I want to show you is the dot product, which is pretty much at the heart of generative AI within transformers. So this thing is used all the time. It's sort of used along with matrix multiplication. So let me kind of show you how this works. So I'm going to create a new array, and I'm just going to do that as before, mx array. I'm going to this time have an array of 1, 2, 3, and I'm going to set the type of this to being, we'll say float 32 at the moment. Now, because I've got an array of 1, 2, 3, what I'm going to also do is have another array of 4, 5, 6. So what the dot product is essentially multiplying all the corresponding elements of the vectors, and then we're going to sum up the result. So in this case, it's going to be 1 multiplied by 4, and that's going to be added to 2 multiplied by 5, and then that's going to be added with 3 multiplied by 6. So if we do that calculation for a second, 3 multiplied by 6 is going to be 18. 2 multiplied by 5 is 10, so that's going to be added together. That's going to now be 28, and 1 multiplied by 4 is 4, and we add that on, and that's going to be 32. So to achieve that, not only am I loading my array as I did before, but now what I want to do is do a C equals mx dot mat mul, and that's a matrix multiply, and then I'm going to pass in A and B. And now if I was to print this off, and we just do a python.scratch.py as we did before, you can see 1, 2, 3, 4, 5, 6, and there you go. It's done the matrix multiply, so it's done the dot product, and it's came back with the answer 32. And that is probably one of the core things that is going to be used within transformers. It is used all of the time. You will see this. It's just this idea of a dot product. Again, super simple to achieve in Apple MLX, and again, super simple to achieve in TensorFlow, NumPy, etc. So now that we understand the dot product, if I wanted to, I can put in a kind of pure matrix multiplication example. So to do that, rather than dealing with single column vectors, we're just going to add in a couple more dimensions here. So rather than having 1, 2, 3, I'm going to do this as kind of 1, 2, 3, 4. Then I'm going to copy this down here, and we're going to make this 5, 6, 7, and 8. So now if we multiply this together, you can see it's came back with 19, 22, 43, and 50. So matrix multiplication works in this sense. Again, you're going to see matrix multiplication happening all of the time. If you want to calculate how that actually works, remember what I said, it's the rows multiplied by the columns. So 1 multiplied by the 5, right, plus 2 multiplied by the 7. So 2 multiplied by 7 is 14, 1 multiplied by 5 is 5. You add them together, that gives you the 19. So now to get to the 22, we're going to do something similar. It's the 1 multiplied by the 6 plus the 2 multiplied by the 8. Remember, rows multiplied by columns. Add that together, you're going to get 22. Now, if we want to look at the 43, we're just following the same thing here. So it's going to be the 3, and then that's going to be multiplied by the 5, and it's going to be added to the 4 multiplied by the 7. And then that's going to add that together, and that's going to give you the 43. And then for the 50, it's the same thing again. So we're going to take the 3, we'll multiply by that by the 6, the 4 multiplied by the 8, they're going to be added together, and then it's going to give you the 50. And that is matrix multiplication, which is essentially just calculating the dot products of the rows of the first matrix with the columns of the second matrix. And then finally, if I wanted to, because again, if you think about what's going on when you're dealing with large language models, you can actually do it in batches as well. So in the same way as we did 1, 2, 3, 4, blah, 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 we can actually have batches of this as well. So rather than me having to loop through things, I can just provide all my matrix calculations in batches. And then if I were to run that, you can see it comes back with the batch calculations there with the results of each one. So take a breather for half a second there. But as you can see, it builds up quite nicely as I'm pushing a lot of things onto the GPU. I can do batching, I can do operations, I can do the dot products, I can do matrix multiplications. Again, these are concepts to get fairly familiar with, but Apple MLX handles it quite well. And then you can do the same things in things like NumPy, and you can do the same things on Torch as well. This is the heart of what you are doing when you deal with a large language model. Once you get comfortable with those concepts, everything that you see, and when we talk about in future videos, like how layers are handled and how transformers work, underneath this is just those very same operations that I showed you. It's matrix multiplications, it's dot products, it's doing things like on batches, it's loading those data into tensors. That's really it. So probably you've got the idea of operations. Probably the other thing that I want to be able to show is how you are able to kind of shape some of these vectors and matrices. That's probably going to be really important as you build this out as well. So I'm just going to get rid of this for a second. And we're just going to create a few shapes here. So the first one I want you to be aware of is a thing called the A range. So if we do mx.arange, and then I am just going to pass in a couple of values. So what A range does is it will just generate a range of numbers. So I'm going to generate numbers from 10 to 60 or 10 to 50. So that 10, 20, 30, 40, 50 that you saw early. So the start number is 10, the end number is 60, and then my step is going to be 10. So if I run that for a second, let's just clear this, and then we do Python Scratch. You see I've got this array 10, 20, 30, 50. So before I typed it in, but what I'm doing here is just generating this out, and then it's of int 32. So really nice and simple there. Other things you might be able to see is the idea of zeros. So, and I can pass in a shape here. So if I pass in 5, 1, I'm just going to zero out a column vector as we saw before. So we'll just clear this. And then I'll do Python scratch, and you see it's exactly what we had before. But instead of going 10, 20, 30, 40, 50, it's just 0, 0, 0. So this is me zero out an array. If I wanted to use the shape of an existing array, let me just put that A range back in. And now when I do my zeros, so let's do mx dot zeros, and in this case, I'm going to pass in a dot shape. Then rather than me manually specifying the shape, I can pull the shape from A here, and then I'll just print out A and B. So if we just hit save here, we'll clear this, and we'll run this one more time. And you see it's come back with 0, 0, 0, and it's taken the same shape as above there. Probably the last thing that I'm going to show you in this case, and you see this quite a lot in machine learning, is you want the ability to generate some random numbers. I'll do this with integers later on. I'll show you how to do this without integers, with float values. But to do that, I can just do mx.random. And then within here, you can see there's a whole load of different random number generator routines. So normals used quite a bit. Uniform is used quite a bit. I'm just going to, because it's integers, I'm going to use randint. And again, I'm going to generate numbers from 0 to 100. And then I'm going to want to generate this within the same shape as A. So we'll just do A shape. And then if I print this out here, you can kind of see it's just generated random numbers within that shape. And again, this is super useful when training large language models, because what happens, like the zeros, you zero stuff out quite often, but quite often you will just actually initialize some of your tensors with random numbers, and then as the training happens, it will go and find the weights that it needs to become. And again, so when you see that, that's just the way almost every one of these layers work today. Okay, so that's initialization. The other things I'm going to show you is a couple of things of how to reshape some arrays. So in this case, I'm going to have essentially a nice little matrix here with 10, 20, 30, and then 40, 50, 60. If I print that out for a second, this won't be too much of a surprise. There you go, 10, 20, 30, 40, 50, 60. You see, one of the things I've done here is I've added on this little extra dimension here. If I want to flatten that out, I can do something like b equals mx dot flatten. And then I can pass in what I want to flatten out here. So if I do a print b, and then we just run this one more time, you can see that those extra two dimensions are removed, and then it's just flattened down to a single dimension. So that's what flatten does. It just reduces your vectors down into a single dimension there. So I think that's pretty cool. And again, there's also the equivalent of which is squeeze. So if I just add mx.squeeze, and we'll do this on A, and this time I'm going to print C as well. We'll just run this one more time. And you can see flatten has brought it down to one dimension, but you see what squeeze does is it reduces by one dimension. So if I just want to remove one dimension, change the shape there, then that's where I would use squeeze. But if I want to flatten it completely, then I would use flatten. Again, these are things you will use quite a bit when you're working with vectors and matrices within MLX or within numpy or pytorch. Now, of course, one of the things I might want to do is add a dimension. So if I just do D for a second, and then I do a thing called expand dimensions, and then we will just pass in this case, we'll pass in C because we squeezed it. And then I'm just going to add in, I want this added in to the kind of final axis there. I could put -1 if I want it at the beginning, but I just want to add it at the end. So if I now do a print D, it's kind of, think of this as the opposite of squeeze, expand dimensions. And you see there, here's where I squeezed it and I brought it down into 2 dimensions, and then I've just brought it back into adding the extra dimension back on there. So that is all expand dimensions. Other things that you might want to be able to do is you might want to be able to do things like concatenation. So if we just take this and this for a second, let's just bring this down over here. I'm going to create b equals mx.array, and we'll just paste this back in. So I've got 2 arrays, 10, 20, 30, and 40, 50, 60. And all I need to do is do an mx concatenate, and then I'm just going to pass in a list of arrays that I want to concatenate. So I'm just going to pass in A and B within a list here. And now if I just print this out and run scratch one more time, you can see 10, 20, 30, 40, 50, 60, and they just can get concatenated into a single list. And again, it works equally as well with floats. And again, that's something that you're going to see quite commonly when you're working with LLMs. Another thing that you might want to be able to do is you might want to be able to reshape things. So if I just change this and we'll do, let's say we have an array of 10, 40, 50, and rather than making that a row vector, I want to turn that into a column vector. One of the things I can do is then reshape that. So if we just do a b is equal mx.reshape, and then I'm going to pass in a, and then I'm going to pass in the new shape of what I want. So I'm going to want this, there's essentially 5 items in that list. So I'm going to make it 5, 1. So you'll remember that from earlier. It's the same as our kind of column or vectors. And then if we just print this, we'll just clear. And you can see that 10, 20, 40, 50, which was essentially a row vector as we saw before. We've just turned it back into a column vector, 10, 20, 40, 50 there. So again, reshaping is something that you're going to do very, very frequently as well. And then other things that you might want to be able to do is do a kind of broadcast. So if I take this here, this is a 10, 20, 30, for example, and then maybe what I want to do is rather than having a single row of 10, 20, 30, I maybe want to turn it into a 3x3 grid, essentially 10, 20, 30. One of the things I can use is a broadcast. So I'll just do mx and we'll do broadcast 2. I'm going to pass in the array in this sense, which is A, and then I'm going to pass in the new shape that I want it to be. So unlike kind of reshape where I get the reshape, that's fine. But in these cases, I don't have the values to fill that in. And then it's just going to fill this in with the kind of by repeating these values here. So if I just run this one more time, you see that 10, 20, 30 now it becomes 10, 20, 30, 10, 20, 30, 10, 20, 30, and that's a kind of broadcast too. Again, something you're going to see quite often. And then probably one more thing that you are going to see quite often is this idea of transposing. So I've got 10, 20, 40 there, so I'm just going to make this 40, 50, 60, and then I'm just going to do a transpose. So I'll just do mx.transpose. And then I'll just pass in A here, and then we can see what this looks like. So as you see, 10, 20, 30, 40, 50, 60, and now it's became 10, 20, 30, 40, 50, 60. So that 10, 20, 30, which was the row here, is now became the columns, and the 40, 50, 60 here became the column. So I've just sort of transposed. Again, that is something that's used super, super frequently. So just getting used to how this works is really going to sort of help you out there. Now, we talked a little bit about data types before. Just to kind of cover this and square this off before we move on to the next piece is we've been passing through things like int32, etc. One of the things to kind of be aware of is using the right data types really going to help you out from kind of various kind of memory sort of perspective. So if we look at my screen here, I've just sort of marked out kind of int8 down to kind of uint32 there. So you can kind of see the size and it takes up. So an int8 does -128 to 127. A uint16 is 0 to 65,535. So if you think about vocabularies for a second, if you want to save a bit of memory when you're loading this up, for example, if you've got a vocabulary of 50 odd thousand on a kind of tokenizer for an embeddings layer, then you might be able to use a uint16 there and then just take up 2 bytes in memory, which might help you on saving a bit of memory management there for loading that up. Now, when we look at something like floats, for example, quite often you use float32, and we just look at that there for a second. You can see, though, that when we're doing matrix multiplication and where we're storing these weights in memory, float32 is going to sort of take up 4 bytes there, which is quite a lot there. There's a lot of things going on in the industry about using bfloat16 for being able to train models. The nice thing about bfloat16, it is effectively the equivalent to float32, but it's got less precision. But more importantly, it uses up 2 bytes. So that makes it more accurate than a float16. So what that means is that when you're training these models, a lot of people are moving towards bfloat16 to save memory and therefore speed up training time and speed up inference versus using kind of a float32 there, but you've got a little bit more accuracy than a float16. And again, it's just something to be aware of. Nice thing about MLX is it kind of supports that out of the box. So just being able to use the right types in the right scenario is really going to help you out. Now, I want to just sort of bring this a little bit to life in the context of large language models for a second. So one of my previous videos, I covered tokenization quite heavily. So when you're working with large language models, for example, they don't understand text. There's actually a vocabulary there. So you have this vocabulary of all of the items in a dictionary. And then when you talk to the model, what you then do is essentially do a thing called tokenization, where it looks up the dictionary and then it gets the sort of numeric value for this. So in this example here, you see who is Ada Lovelace, who is in a dictionary at spot 11644. So the number for that is that integer 11644, and that happens for everything within here. And again, I have a set of tools that are kind of useful for this, and we'll show how this relates to MLX in a second there. So if I run my print token tool for a second, then I ask it the question, who is Ada Lovelace? This is Llama 3, so it's slightly different. It's exactly what I said there, who is Ada Lovelace? And then you see here is the token in the Llama 3's tokenizer dictionary. And again, that's how things get sort of tokenized. So if we wanted to, we could do the equivalent of tokenization and things like MLX. Again, if you want to implement your own tokenizer, you can do this. But if I take this phrase here, who is Ada Lovelace, which is a sentence, I'm just going to do a sentence split, which is going to cut out the spaces here. So who is Ada? And then Lovelace will be one word. I created a vocabulary here, which is who is Ada Lovelace. So that is token 1, 2, 3, and 4, which is a much shorter vocabulary or dictionary than Llama 3 has, but it's the equivalent. And then if I wanted to, I can just convert tokens into their indices. So I'm just going to loop through all the words in the token there and then print that out. And then if I wanted to, you see here, tensor is equal to mx array token indices. What I can then do is take the equivalent of the phrase, and then I can just load that into an mx array and then print out the tensor. So if I run that for a second within our scratch, and you can see tokens who is Ada Lovelace, token 1, 2, 3, 4, and then the tensor is an array of 1, 2, 3, 4. And this is exactly, if I come back into this example, it's a much smaller vocabulary, but essentially this is exactly how a tokenization works today. So again, when you're dealing with large language models and you're looking at things like tokenizers, that is literally all that's happening from a tokenization. It's just doing that lookup of a dictionary, and then it's loading it into a tensor. And actually, if I kind of wanted to prove it even a little bit further, we'll just do this manually for a second. So I'm gonna bring up Llama 3 within a little script that I've created that uses MLX underneath the hood. So you see it's loading the Llama 3 8B instruct model. I've implemented that. I've loaded this myself with my Chuck MLX framework. And then if I just type in who is Ada Lovelace, which is exactly what we did there for a second, you see it's going to come back with who Ada Lovelace is. It's just streaming this out. So that's all very cool. But if I look at the code underneath that for a second, let's just quit out of this for a second. We'll just type in code dot. If we just go into the infer script for a second there, and if we go to generate response, so we'll just go to generate response. You can see here, encode the prompt, mx array, tokenizer.encode. So it's just doing that exactly what we said there. It's just looking up the dictionary. And then when we go and interact with the model, you see all I'm doing here is I'm doing mx array. I'm actually loading in that tokenized version. So again, when you start to look at this code or you want to start implementing it for yourself, this is literally how it works. So, and then once you then over here, you're going to generate this sequence. We'll talk about that maybe in another video. But when I want to get the output there, all I'm going to do is do a tokenizer decode and it's going to come back with the output. So this is how you work with large language models. And then any inference framework that's using MLX, this is exactly what they're doing underneath the hood. And again, I can go a little bit further as well. So one of the other things we're going to do, this is one of my other tools here. We're going to look at the layers of the Llama 3 8B model in this sense. So you can see here, the very first layer is this embeddings layer. And then I've got 32 layers underneath that. And then I've got finally a normalization layer, an output layer. If we look at what this embeddings layer is for a second, this hopefully will all start to come together. And it's not any different for any of these other layers, by the way. But if I just look at what an embeddings layer is, here's an example. This is actually a Llama 2 example, but it's close enough here. The embeddings layer, which is your first layer of your model, is just the vocabulary of your dictionary. So in the same way as we did who is Ada Lovelace, and we built up a vocabulary, then it's just a dictionary in this sense, and it's a dictionary of vectors. So you see here, 1 has got this great big set of dimensions, 0.1, 0.2, da, da, da. And this should start to feel familiar because it's exactly the same thing as we were doing with vectors a little bit earlier. But for each one of those items in the vocabulary, there is a set of dimensions that are associated with this. And you can actually see this. So if we clear this for a second and then we look at the config here. So again, I'm using a tool, show config there. You can see here that in this particular case, there's the number of hidden layers, which is 32 in this sense. But the number that you're most interested in here is the thing called the hidden size. So intermediate size is going to be the size of the dimensions for each one of the hidden layers. But for that first layer, the embeddings layer, it's this hidden size it's defining. So in the case of Llama 3.8b, it's going to be of a size 4096. So that is, and again, this is just the same stuff as we were showing you earlier. So if I was to clear this for a second, actually, and then the final thing is the vocab size. So you see in this case, it's a large vocab, 128256. But if I was just to clear this, if we wanted to, we could actually manually create that embeddings layer. So I'm just going to do import MLX core. You see the vocab size is 128256. The hidden size is 4096. So remember, it's a dictionary, or with each item being an item in the vocabulary, with the hidden size being the size of the dimension there. So I'm just going to do I'm going to randomly create, I'm doing an mx random.normal. We talked about that earlier. And it's just going to generate a random number. It's fairly big, right? 128256 multiplied by 4096. And then we'll print out that shape. And then if we want to batch, if we want to do a batch lookup of what the embeddings are for each one of these, which is we're randomly generating, then we can pass in the values that we want. So who is Ada, blah, blah, blah. And then manually look up those embeddings and get the input indices and then print that out. So if I clear this and do a Python scratch.py, you can see here the shape here is 1282564096. And then 4096 is for the batch that we just created. And then literally it's going to walk through that batch and pull back the dimensions for each batch there. And again, these were randomly generated, but this is exactly how an embeddings layer works. This is how it's represented. Just rather than it being random numbers, it's going to be things, it's going to be features that are correlated to each other. And I do a whole video on kind of the features of embeddings and how you can do cosine similarity searches, etc. Go check out that video. That's really how an embeddings layer works. And again, if you've been sort of looking at things kind of from a torch neural network, or if you're looking at MX from a neural network perspective. But now if I was to look at it, if I come back into my Chuck MLX framework for a second, and I'm going to pick one of my existing Llama architectures here. So I'm just going to go to my transformer base model. What I want you to see here, that this is a transformer base model class. I'm inheriting from nn.module, which is part of MLX NN framework. But the key thing I want you to see here is when I set my embeddings layer, this is creating an embeddings layer at this point. You see, I'm just making it equal to nn.embedding, and I'm passing through the vocab size and the hidden size. That's all it's actually doing underneath the hood for that embeddings layer is literally doing what I just showed you, which was randomly initializing the vector and creating one of that size. So that's really how embeddings layer work. And then you can kind of see here, it does the same for attention layer. Again, if I were to scroll through some of this stuff here, again, I'll maybe do another video on this framework at this point. But kind of what I want you to see there is most of the stuff, everything that I've kind of shown you today is the stuff that you're going to be using there. So there's an mx.add, there's another mx.add. As we're sort of trying to sort of train some of the models there. If we come into my attention base here, you can kind of see I'm working with MX arrays. There's a reshape because we're going to reshape for the QK and V heads there. You can see I'm doing MX concatenates there. So, and then I'm using kind of an MX fast scale dot product attention, which is a slightly faster way than what I was showing before. But again, this is just using some of the stuff in MX framework. And again, if I look in here in my transformer block where I'm doing inference, you can start to see that Other things I'm using is span dimensions, broadcast, MX multiply. So everything I've shown you today in MLX framework is actually what is being used when you implement a transformer underneath the hood. Again, I'll probably do a video on this framework at some point as I've sort of built it out, but hopefully these things should start to become kind of familiar in that sense. So I think we're sort of coming to the end of this. There's maybe one or two more concepts I want to go through, and then we'll call it a day. I think the first thing that I want to say, and maybe I should have covered this earlier on here, is that when we're working with MLX, one of the things that it actually does is lazy evaluation. So when I do Python scratch .py there, you can see it's coming back with the answer. But the reason it's coming back with the answer is because I've run a print. If I don't run that print, that's the point where it gets evaluated. So even if I did a kind of, let's say I did a B here, for example, and we did a B MX array here, and then I run that print, this never gets evaluated, right? Because there's nothing that's doing any evaluation. Only A will get evaluated on the print there. So if I run this here for one more time, you see it's come back with 10, 20, 40, 50, 60, but it's never evaluated this piece because it uses lazy evaluation. If I did a print B, it would get evaluated, or the other way I could get it to evaluate is if I do an MX .eval and then I pass through B there, then at that point it would evaluate it regardless. So it's just something to be aware of, that it uses lazy evaluation underneath the hood. So as you train these things, then just kind of be aware that, you know, accessing it via an index, doing a print, whatever, that will kick off an evaluation automatically. But if not, then you might need to do an MX eval. And again, there's a bit of a trick of when to do this and when to not. The other thing to be aware of as well, and I'll do this with the print A and print B in this sense, is with MLX, Apple uses unified memory. So actually, unlike Torch, you often have to decide which device you want it to run within. And then it will swap memory, so you can sort of move from the CPU memory to the GPU memory backwards. Because Apple has unified memory, you don't need to do that. So both CPU and GPU has access to the memory. Now, what makes this super powerful is I actually can specify whether I want this to be run by CPU or GPU without having to move it from memory. So let me show you what I mean. So if I do a C equals mx.add, just as we did before, I'm going to add A to B. But one of the things I can specify here is I can just set the stream, and then I can say this one is going to be equal to mx.cpu. And then, of course, if I want to do the same thing, but this time do it on GPU, we can go AB, and then this time I can say stream is equal to mx.gpu. So I can be explicit. Now, of course, you know, by default, it's obviously GPU, but again, you can sort of move your workload across there, but I've not had to move anything from memory because it's a unified memory. So if I now come back into my command terminal, and then I type in Python scratch here, you can see it's done all the calculations. It just happens to be that third one was done on CPU and the other one was done on GPU. And then probably one other thing that I want to kind of show here is I can obviously do saving as well. So if I want to, I can save this to something like an MPZ file, and that makes it sort of numpy compatible. So I can go test.mpz. Then if I want to, I can reload it as well. So again, that is quite useful because everything is kind of numpy compatible. So anyway, I think this is all I wanted to cover today. I know this is a super long video, but I'm hoping that this helps you get really super familiar with Apple MLX. I hope it gives you a good idea of what large language models are using underneath the hood and kind of what concepts you need to be able to understand and utilize. In a future video, I'll probably go into a little bit deeper on how to train a large language model, which I think will be cool. And again, just having a familiarity of MLX will sort of help you in that. Anyway, I hope this video has been useful, and I will catch you on the next one.